Okay, in this lab we are going to try and figure out what happens in collisions, and we're going to extend some of the ideas that we learned in the previous class. So let's kick it off with a description of how we will go about it. So this here is the display control, and essentially I'm going to keep this momenta diagram and kinetic energy checked. The kinetic energy will show me what the total kinetic energy is over here. Momenta will show me what's the total momentum. Yeah. Then in this input data box, I'm going to click more data, and that allows me to input masses, positions, and velocities for these balls 1 and 2 over here respectively. That's before the collision, and calculates the momentum at any point in time. This elasticity slider here lets me decide whether the collision will be elastic or inelastic, and if it's inelastic, then to what extent. If I push the slider all the way to the left, that's a perfectly inelastic collision. All the way to the right will be an elastic collision. This lets me set the simulation speed, and I'm going to kind of set it about a quarter of the way or 20% of the way so that we can see what's happening. The play pause button allows me to start and pause the experiment, and restart brings me back to these initial conditions that I specify here. So those are our controls that we have. Let me start. As I said, I've checked these two. Note that the elasticity slider is all the way to 100% elastic. Now let's set our input data. Let me set the mass of ball 1 as 1 kilogram, mass of ball 2 as 2 kilograms. Okay, I'll leave the positions as they are, and I will set the velocity of ball 1 to 1 meter per second and that of ball 2 as 0. Now let's look at the momenta, the calculated momenta over here. As we can see, the momentum of the first ball is 1 kg meter per second, and we get that simply by multiplying the mass times the velocity. Yeah. For the second ball, the momentum is 0, and we get that simply again by multiplying the mass 2 by the velocity 0. Let's look at the momenta diagram, and as you can see that there is only one momentum over here, and that pertains to ball 1. The pink arrow represents total momentum that pertains to the sum of ball 1 and ball 2. In this case, ball 2 is 0, so it's just ball 1. So that's our starting point. Now let's look at the initial kinetic energy before the collision, and that works out to 0.5 joules. Yeah. So now what we're going to do, let's see how we would calculate this. Give me one moment, please. So here we go. I'm going to show you how this number is calculated. We start drawing. Okay, so here we go. Essentially we've got only one ball. Yeah, so kinetic energy equals half mv squared, and since we've got only one ball, that's the kinetic energy of just one ball. That's equal to 1 by 2. Mass of the ball is 1 kilogram, velocity of the ball is 1 meter per second squared, and that works out to 0.5 joules. Yeah, and that's what we got here as the kinetic energy of the ball. Alright, so we've done that much. Now let's move on. I'm going to press this play button here and let the collision occur, and then we're going to, I'll pause it right after, a few seconds after the collision to see what happens. Here we go. That's the collision occurring, and now I'm going to pause it. Okay, so what happened? Let's take a look. First, let's read off the kinetic energy, and we can see that it's still 0.5 joules after the collision. Note our elasticity setting, and we've specified that it's an elastic collision. Now by definition, that means that kinetic energy is conserved, which means that this kinetic energy remains at 0.5 joules. Now let's read off the velocities of the two balls. As you can see, the first ball rebounds backwards. Its initial velocity was 1 meter per second. Now it's become minus 0.33, and the second ball gets a velocity of 0.67. Okay, these are the momenta, which is mass times velocity of each of the two balls over here, and if we add them up, we can see that the total momentum, remains minus 0.33 plus 1.33 works out to 1 kg meter per second, and therefore we can see that momentum is also conserved. Alright, now let's set the elasticity slider somewhere around 75%, yeah, somewhere around there. Let me press restart, and that brings me back to the initial conditions, which is exactly the initial conditions before the collision in the previous experiment. And you can see that the velocity was 1 meter per second to the right for ball 1. Momentum is 1 kg meter per second, only ball 1 is moving to the right. You can see that here. And you can see that kinetic energy still remains 0.5, which were the initial conditions in the previous experiment. Now, again, I'm going to press play. I'm going to pause the experiment after the collision, and let's see what happens. Here we go. There, I pause it. And now let's see what happened. First, take a look at the kinetic energy. It's now 0.35 joules. Okay, which means that kinetic energy has now fallen as compared to the 0.5 joules we had to start with. And that is to be expected. Why is that? Because we had said that the collision is not 100% elastic, which means some of the kinetic energy is lost as heat or as light or something else. Yeah, some of the kinetic energy is lost. The idea is in a collision that is not perfectly elastic, i.e. an inelastic collision or a partially elastic collision, total energy is not conserved. Is momentum conserved in an inelastic or partially elastic collision? Okay, let's see what the final momenta after collisions are. Here are the velocities that are computed, and here are the momenta. As you can see, momentum for ball 1 is minus 0.17 kg meter per second. For ball 2 is 1.17 kg meter per second. Add them up and you should still get 1 kg meter per second, which means that momentum is conserved. So what's the conclusion that we come to? In a collision that is partially elastic, kinetic energy is not conserved, but momentum is conserved. In a collision that's fully elastic, which was the previous experiment that we did, momentum is conserved, kinetic energy is also conserved. Look at this momentum graph here on the right, and you can see that you've got a positive momentum from ball 2 after the collision, a negative momentum from ball 1. Add these two up and you'll find that this is the same as what we had earlier, which was 1 kg meter per second. Okay, now let's do something else. Let's move this elasticity slider all the way down to 0. Okay, which means that it's a perfectly inelastic collision. Let me press restart, and that brings us back as usual to the starting data before the collision that we had entered. Again, I'm going to press play, let the collision occur, and then pause it a few seconds after the collision finishes, and then we can see what happens in this case. Here we go. 1, 2, 3. That's the collision occurring now, and take a look. Let me pause it. Let's look at the velocities. Let's first look at velocities. Velocity of ball 1, 0.33. Velocity of ball 2, 0.33. What does this mean? It means that both balls have the same velocity in the same direction. What does that mean? Anybody? Exactly, they are one body in effect. Okay, it is one body. They've stuck together after the collision, and therefore the velocities are the same. Okay, and that's what happens in an inelastic collision. In an inelastic collision, the two bodies stick together and move with the same velocity. Let's see whether momentum is conserved in an inelastic collision. Let's look at the momenta. Momentum of ball 1 is 0.33 kg meter per second. ball 2 is 0.67 kg meter per second. Add them up and we will still get 1 kg meter per second, which was the momentum before this collision as well. And we can see that now from the momentum graph here, that both bodies have momentum in the same direction, but the total is the same as what it was earlier, 1 kg meter per second. Okay. Now let's look at energy. Is kinetic energy conserved? No, it's not. When we started, we had 0.5 joules. Now what we are left with 0.17 joules, which means that kinetic energy is not conserved. So again, to summarize, in an inelastic collision, kinetic energy is not conserved, but momentum is conserved. Now you can use this to create all kinds of experiments for yourselves. So for example, let's say you want, and you'll find some of this in the quiz associated with this lab. So essentially, let's say you want to figure out what happens to an auto rickshaw, okay, when a truck hits it, for example. So let's model that, and let's kind of call ball 1 20 kilograms. So that's the truck. Let's say it's moving with a velocity of 1 meter per second, yeah, and we'll model the auto as a really small mass, 0.5 kilograms, and it's also moving to the right with, let's say, with a velocity of 0.5 meters per second. Okay, and let's make this 2 just to speed up the experiment. Okay, and so these are our initial conditions. Let's say, and let's set the elasticity somewhere in the middle. That's what happens in real life collisions. It's partly elastic, partly inelastic. So let's see what would actually happen were something like this to happen. Okay, I press play, we let the collision occur, and I pause it. Let's see what happened. As you can see, the velocity of the truck has hardly reduced, from 2 to 1.94, but the velocity of the poor auto has jumped almost 5 times. Yeah, so clearly you can figure out what might happen in such a collision. You can model that. Yeah, it's clear that the auto will go flying and almost nothing will happen to the truck. Okay, so you should be able to kind of guesstimate that there should be a fair bit of damage to the auto rickshaw. Okay, all right, so that's the collision lab. There are a number of questions on this in the quiz associated with this lab, and you should be able to do those for yourself. Let's set up another lab, and this time this is the balancing act lab over here that you can see. Yeah. Now let's do the so let me again, as usual, describe. This is the display control, and we are going to set all these to on. Okay, this is the level indicator. That's the ruler which tells us how far to the left or right of this fulcrum we place the masses. These are the supports. If you take these supports away, then the balance, then we'll see what happens, whether we can maintain balance or not. These are the masses available to us: 2 fire extinguishers of 5 kilograms each, and 1 garbage bin of 10 kilograms. Okay, that's the reset all button, and we can remove supports and you can add them back as well if you press the same button. Okay, so now let's see what happens. We take this mass and move this to on the left hand side of the fulcrum to the 1 meter position. So this distance is 1 meter from the fulcrum. All right. Now, what happens if I remove these supports? What will happen? Okay, let's take a look and see. We should be able to see quite clearly that there's a mass only on this side. So there's an anti-clockwise turning moment about the fulcrum. And if we remove these supports, then we should see the seesaw tilt towards the left. Let's see if that's what happens. I click remove supports, and that's exactly what happens. Okay, so this should not be any surprise at all. So really, if we had to calculate what this moment is, and let me come back here and calculate what this moment is, and so the turning moment, which is anti-clockwise, is going to be equal to the mass So times G, this is the force acting downwards. Now I want you to remember that this is not the weight that's acting down. This really is the normal force of contact between the fire extinguisher and the seesaw. How do we figure that out? Let's draw the FBD for the fire extinguisher. Its weight acts downwards and there's a normal force acting upwards. Yes? Now, because it is stationary, weight equals normal force. Alright? Let's draw the FBD of the seesaw. And since its weight is supported, we're not really concerned about that. Let's just worry about the normal force. Yeah, and so the normal force, every action has an equal opposite reaction. So this normal force acts downwards when it acts on the seesaw. So this force that you're talking about is not the weight, it's the normal force, but it turns out that it's equal to the weight of the fire extinguisher. But that's just by coincidence, okay? As an example, so many students get into this confusion of assuming that weight acts on the seesaw. The weight of a body can never act on anything else. It only always acts on on itself. Okay. As an example, think about an inclined plane. Okay. Now, if the weight is like this, okay, if a block is like this, the weight acts downwards, but the normal force acts perpendicular to the surface of contact, and therefore weight in this case is not equal to normal force. So if you make the assumption that whatever acts on the seesaw is weight, you will make a mistake in the case of an inclined plane like this. Okay, so keep that in mind. Draw the free body diagram and you'll see that what acts on the seesaw is this normal force. Okay, so anyway, back to what we're trying to do. Here's the anti-clockwise moment. That's the normal force times the distance, and in this case mass is 5 kilograms, acceleration due to gravity is 10, and the distance is 1, so you get 50 Newton meter anti-clockwise. Okay, this is the anti-clockwise turning moment, and that's why the seesaw tilts towards the left. That should be pretty straightforward to understand. Now let's see what happens. Now what I'm going to do is I'm going to place another mass, identical mass, 1 meter to the right. Okay, this time if I remove supports, what will happen? In this case nothing should happen, because the turning anti-clockwise, the clockwise and the turning moment anti-clockwise equals the turning moment clockwise. Yeah, and both are equal to 5 times 50, that's equal to the normal force, multiplied by the distance, which is 1 meter for both cases, but they act in opposite directions. One is clockwise, one is anti-clockwise. So if I remove supports, as you can see, the seesaw stays level, nothing happens to it. Okay, let's add the supports back, and now let's try and do something else. Let's take this 5 kg mass and put it at the 2 meter point on the left of the fulcrum. Let's take this 5 kg mass and put it at the 0.5 meters. Now what will happen if I remove supports? Let's try and do the calculation separately first, okay? So let's try and figure out, we might understand it intuitively, but let's do the calculations. Let's calculate the turning moment anti-clockwise, and that's going to be equal to force times distance. Force is equal to normal force, which is equal to weight, which is equal to mg. So that's m is 5, g is 10, and the distance is 2 meters. Okay, and the anti-clockwise moment, therefore, we can see is 100 Newton meter. Okay, now if we take the turning moment clockwise, the force is the same because the mass is the same of the fire extinguisher, but d2 is different, so it's 5 times 10 times 0.5, and that's going to equal 25 Newton meter. Right? Now Clearly, the anti-clockwise turning moment is greater than the clockwise turning moment, and therefore we would expect the seesaw to tilt towards the left. Let's see if indeed that's what does occur. I remove the supports, and exactly that's what happens. It tilts anti-clockwise, or the left side goes down. Okay, so let me add back supports, and let's do something else now. Now let me move this 5 kilogram mass to the 1 meter point, while keeping the 5 kilogram mass on the left hand side at the 2 meter point. Now I have got this 10 kilos. Okay, now, well, let me put it like this. It's fairly clear that in this case also the seesaw will tilt towards the left. That should be quite obvious from very similarly as the previous one, same calculations. The question is, where do we place this 10 kilogram mass to make sure that it stays level? And first let's do it by trial and error, and then let's verify our calculation and see whether it's correct or not. So let me start by putting it at, let's say, the 1.5 meter mark. Let me remove supports, and that doesn't work. We now move and tilt towards the right. So now I obviously need to reduce the turning moment to the right. I can't change the masses, I can only change the distance, so I reduce the distance. I move it to 1.25. Does that work? That doesn't work either. So I need to reduce the right hand side moment, or the clockwise moment, a little more. So let me move this to 0.25. Yeah, the least possible, and see if this works. I remove supports, and now it tilts the other way. So I've reduced it too much. That's what it means. So let me add the supports back. Let me move it to 0.5 and see whether this works. And we can see that's exactly what works. Okay, so let's verify why this is so. Let's look at the positions. We've got 1 5 kilogram mass at 2 meters on the left hand side. On the right hand side, 1 5 kilogram mass at 1 meter and 1 10 kilogram mass at 0.5 meters. So let's verify the calculations. Okay, so let's calculate the anti-clockwise turning moment first. So turning moment anti-clockwise equals force times distance. Again, that's simply 5 kg into 10 meters per second into the distance, which was 2 meters, and that works out to 100 Newton meter. The anti-clockwise turning moment is the sum of the two weights, or the moments due to the two weights on the right hand side. So I write it as F1 D1 plus F2 D2. F1 is the 5 kilogram mass times 10, so that's the force, 50 newtons. It's 1 meter away, plus the second mass is 10 kilograms, G is 10, and let's call this X. Yeah, how far away we need to place it. Now this, for balance, turning moment anti-clockwise must equal turning moment clockwise, and turning moment anti-clockwise is 100, so I'll write this as 100 equals to this. Let me simplify. 100 must equal 50 plus 100 times X, and if I solve for X, X is equal to 50 by 100, which is equal to 0.5 meters, which is exactly what I got by experiment, right? So now let's see what happens in another case. Okay, and let me add the supports back. I'm going to use for this the Balance Lab tab, which is identical, except that we use weights instead of fire extinguishers and garbage bins and so on. Yeah, so I'm going to check all these four. So we have your setup. Let me take this 20 kilogram mass and move it to a point 0.5 meters on the left hand side. Okay. Now I take the 15 kilo mass and I want to figure out by trial and error what happens. So let's see what happens first with trial and error. Okay, experimentally let's verify. Okay, so that's not right. Let me move it to 1.25. That's not right either. How about 1? No, that's not right either. How about 0.75? That doesn't work either, but I'm getting close because it doesn't move by that much. And let me move it to 0.5. and now it moves the other way. So clearly from experiment I can see that the correct value is somewhere between 0.5 and 0.75. Since I can only move this in increments of 0.25 in the experiment, I can't find the exact spot by experiment. I just know that it's somewhere between 0.5 and 0.75. Let's see if I can figure this out precisely using the calculations that we're now familiar with. Okay. So the turning moment anti-clockwise, 20 kilograms times acceleration due to gravity times 0.5 is the distance from the fulcrum. And that works out to 100 Newton meter. Turning moment clockwise must equal, we're using a mass of 15 kg. Again, acceleration due to gravity is 10, and let's call this x. For balance, turning moment clockwise must equal turning moment anti-clockwise, so this must equal 100. Now if I solve for x, I get x equals 100 by 15 times 10, which equals 2 by 3, which equals 0.67 meters. This lies between the 0.5 and 0.75 that we figured out experimentally, so we can say that this is the correct answer. Alright, and we've used theory to arrive at the correct answer. We've used experiment to guide us, but theory was able to give us a more precise, exact answer. That's the end of this lab. There will be a quiz which is based on these experiments. If there's any questions, please ask. Otherwise, you're free to leave.